So this is a walkthrough for some of the key ideas for the AQA A-level chemistry atomic structure topic. It's broken down into 3 stages. In this section, we're going to focus on electron configurations, etc. In part 2, we are going to take a look at ionization energy, and in part 3, we will take a look at mass spectrometry. I think it's a really important topic. It's one of those that really applies many of the fundamentals that we come back to and revisit in all of the other areas across the 2-year course. So, I'm going to recommend that you pause as you go through the video, try and answer these questions, try and work out what you know and what you're less confident with, and then you can go and get that help and support from people you need to if there are things that aren't quite clicking into place. So in the first instance here, we have got some prior knowledge. A lot of this topic is prior knowledge from GCSE and taking on some of the keywords that we're hoping that you are going to go on and remember. So take a little bit of time to see if you can match these up, and then we'll see if you've hit the right ones. I will be colour coding them as we continue through the video. So pause, and when you're ready, carry on and look at the answers. So in the first instance, we've got nucleons. Now that's a name that is given to the protons and neutrons simply because they're found in the nucleus. Not a hugely commonly used word, but one that is worth being familiar with. When we get to an element, we're really getting into key definitions now. An element is something that only contains one kind of atom. So lithium contains only lithium atoms. Molybdenum contains only molybdenum atoms, for example. When we move on to electrons, we're going back to GCSE again here. We need to remember that they're found outside the nucleus. They're found in the principal energy levels, commonly known as shells. And we need to know that their mass is negligible and their charge is negative. And we're going to review that as we carry on through this part of the topic in this video. When we move on to an atom, the atom is something that consists of the nucleus with the cloud of electrons, and we know they're moving around the nucleus. We may be building on the model that you've used at GCSE. It's not quite as straightforward as electrons orbiting a nucleus. When we get to compounds, there are some similarities between compounds, mixtures, and molecules definitions we need to be familiar with. So a compound is more than one type of element, and they are chemically combined. Whereas when we look at a mixture, it's more than one type of atom, or it could be compounds, and they are mixed together, but they're not chemically combined. So air is a prime example of that. Air contains nitrogen, which is an element. It contains oxygen, which is an element. It contains argon, which is an element. But it also contains carbon dioxide, which is a compound. They're not combined with each other. They are separated. They are mixed, but they're not chemically joined. When we move on to the next word, which is neutron, again, this takes us back to that table that you'll be familiar with or get familiar with again from GCSE. Found in the nucleus, they have no charge and a mass of 1 atomic mass unit. And a proton, similar pattern, found in the nucleus. This one has a positive charge. It has a mass unit of 1 and it's found in the nucleus. And then we have got molecule. Now, if you take a look at molecule and take a look at compound, you will see that there are similarities, but there is a significant difference. A molecule is 2 or more atoms that are chemically combined. Remember, a compound is 2 or more types of atom chemically combined. So a molecule can be an element. The key examples here are the diatomic molecules. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine. You can actually see those in a pattern on the periodic table, and you will need to remember that they all exist as diatomic molecules. But they are atoms that are chemically combined, but they're not different types of atom. By that same token, every compound is a molecule, because every compound does have more than one atom. It becomes a compound when there is more than one type of atom. Okay, going to move on, and we're going to take a look, again, a chance for you to try here. In terms of the bits of the table in white, all of the information is provided in the blue box, so it is just about moving that into the right places. But have a think about the questions, have a think about filling in what you know, and we'll take a look at the answers in a few moments. Okay, so why do we use relative masses and charges rather than actual masses and charges? The answer is really simple. The values, as you can see within that blue box above, are incredibly small. Masses in the order of 0.911 by 10 to the minus 31 kilograms. That isn't very useful. Now, I've taken the values and put those in, but again, we don't need to learn them. What's important is that you can see that the mass of the proton and the neutron are identical, and the charge on the proton and the electron are equal in magnitude, but opposite signs. That allows us to go to the relative masses and relative charges. So what you need to remember: relative masses are 1, 1, and I've put the actual figure in there, 1 over 1840. I've said in the blue box 1 over 2000. You just need to know it's negligible. It's significantly smaller than protons and neutrons. When we get to the relative charge, you can see that you need to remember that proton positive, neutron neutral, electron the other one, negative. So +1, 0, -1. You have to know it. You have to remember it. And the location we've talked about already. Protons and neutrons are the nucleons found in the nucleus, whereas the electrons are found in the principal energy levels. And we're going to develop that idea a little bit more as we go through the rest of this topic. Okay, for the next one, then it's using the periodic table, using it to find protons, neutrons and electrons. Have a think about each of these questions and then review when you're done. So, in the first instance, I'm going to fill in two of them, the proton and the electron. Remember that the atomic number is the number of protons, and you also need to remember that in an atom, the number of protons is equal to the number of electrons. That changes in ions, and again, we'll talk about that later and in the bonding topic. To work out the number of neutrons, well, the mass number is protons plus neutrons. So to work out neutrons, you have to do mass number, take away atomic number. It's a nice, simple calculation. It's a relatively simple mark to pick up, and having the confidence to do that is going to give you the confidence to build on that knowledge to take on some of the more complex ideas later. So this final question: why an atom will always have a charge of 0? Well, we can see here that the protons' numbers are equal to the electron numbers. There are 3 of each in lithium. We also know from the table that we looked at previously that the charges are equal in magnitude, but opposite with their signs. So if I've got 3 positives and 3 negatives, the charges cancel out. That's why an atom will always have a charge of 0. Okay, we're going to move on to some A-level standard work now, really developing new ideas. And this is a chance for you to think about some of those key ideas and take on some of the wider knowledge from other science areas too. So have a think about these questions and we'll review in a second. Okay, so I'm going to put my answers in the initial answer box. It's one of those where you might amend your answers, you might realise you weren't quite there, and you can put your ideas in. But hopefully this is building on your thoughts, not just telling you the answers. So protons and neutrons are held together by nuclear force. They're in the nucleus. The clue is there in the name. And protons and electrons, well, protons are positive, electrons are negative, oppositely charged species attracting have electrostatic forces. So which of those is stronger, and how do we know that? I've said why there, but it's how do we know that? What evidence do we have? Well, the correct answer is that nuclear is much harder. Electrostatic forces are overcome all the time. Every time metal reacts, it loses electrons. That means the electrostatic force between the nucleus and the electrons has been overcome. It takes much, much more effort, and you'll have done work on nuclear fusion, nuclear fission in physics to know that that is much harder to do. For the next one, I will be absolutely honest with you, I am not going to draw all 20 of these for you, but we do still need to be familiar with the GCSE model for electron configurations. So I'm going to do a couple of them once you've had a go at thinking about these for yourself and to check that you're on the right lines. So, taking a look, we have got hydrogen with 1 electron. Now we know the first principal energy level can hold 2 electrons, so I put my 1 electron in there. Similarly, helium with its 2 electrons, they both fit in principal energy level 1. But I'm going to jump all the way to calcium now. Calcium has 20. So, my first principal energy level holds 2. My second holds 8. And we know from GCSE that we then have 8 more in the next principal energy level, and we have 2 more in the principal energy level that follows. As I say, this is a model that we're going to change quite significantly over the course of the next few minutes. Taking a look at these questions, see what you can do. We're back to GCSE here, really. So how does a group number link to electron configuration? Well, the group number is equal to the number of electrons in the outer shell. So obviously transition metals slightly different, but group 2 have 2 electrons in the outer shell. Group 6 have 6. And then for the charges, it is helpful to remember that group 1 forms +1 ions because they would lose 1 electron. Group 2 forms +2 because they lose 2 electrons. And this table down at the bottom, good practice for using the periodic table. I'm going to put in the data based on the information that we have. So I'm using whatever figures are in there or symbols, and we can see the names. Now, actually, for the one with 14 neutrons, that could be silicon or aluminium. Both are valid. Both have 14 neutrons. I'm going to do it for silicon. But let's see if we can see some patterns. In terms of the symbols, we go straight to the periodic table. People often get a little bit confident on this and then get mixed up. One of the big areas is around fluorine. It is not Fl, it's just F. Atomic numbers, straight from the periodic table again, and I've added those in. But remember that the atomic number is equal to the number of protons, so I can just transpose that column into the number of protons column as well. And we also know that the number of protons in an atom is equal to the number of electrons. We've now got 3 identical columns. I then get the mass numbers from the periodic table, and remembering what we spoke about earlier, we are going to find out the number of neutrons by subtracting the atomic number from the mass number. So I've done that for all of them bar 1, and I left hydrogen till last because hydrogen is a curious element. Hydrogen has got an atomic number of 1 and a mass number of 1, which actually means it's the only element that has no neutrons. Still on GCSE, we're going back to talk about isotopes now. Have a read through these questions, think about them, pause until you're happy, and then go on to review what you've done. So I've got 3 isotopes of hydrogen here: hydrogen, deuterium and tritium. In GCSE, we learned about isotopes. What do isotopes of the same element have in common with respect to their structure? So they have got the same atomic number, but that doesn't tell us about the structure. It tells us that it has the same number of protons and it has the same number of electrons. So always be mindful of how the question is being asked. But what about properties? Well, they're going to have identical chemical properties because chemical properties are determined by electrons being lost, gained or shared. They're also going to have very similar physical properties. There may be incredibly slight variations, but not much at all. So what are the key differences? Well, we've got a different mass number, a different number of neutrons. The number of neutrons is what will determine the variation in the mass number. Hydrogen is hydrogen because it has 1 proton. Hydrogen has 1 electron because it has 1 proton. The neutrons that don't really do much are what then bulk out the mass. So we're going to move on now and we're going to take a look at some more challenging content. We're moving into A-level territory. Fundamental principles, and I want you to pause this, read it through, and we're going to pick out some of the key ideas. Okay, So we have talked about electrons being in shells or energy levels. We can actually break that down into smaller subgroups. Energy levels are broken down into sublevels. Sublevels are broken down into orbitals. You are going to have to remember the different types of sublevel that exist, how many orbitals they contain, and how many electrons they can hold. All of that is going to allow you to take on the new A-level challenge of electron configurations. So, at GCSE we learned that the first principal energy level holds 2 electrons. We know that and we've spoken about it already. Now it's made up of an S sublevel. This is really important because you now know how many electrons an S sublevel can hold. You're also being told here that an S sublevel contains 1 orbital. That's also really useful because we now know how many electrons an orbital can hold. So we're going to take that information and try and drive this forward. To summarise, the first principal energy level contains 1 S sublevel, so it can hold 2 electrons. That S sublevel is made up of 1 orbital, and an orbital can always hold a maximum of 2 electrons. Now let's move on to principal energy level 2. We know, I'll let you pause actually. We know that the second principal energy level can hold 8 electrons. Now, we know that in the first one we had a 1s. The s is the sublevel, the 1 is the principal energy level. So what we've got here is a 2s sublevel. You're asked if you think it will be bigger or smaller than 1s. Well, we know that as we go into subsequent energy levels, they are bigger. Electrons are further away from the nucleus. So it stands to reason that the 2s is bigger than the 1s. Now it also contains a p orbital, and it only contains a p orbital in addition to the s. So how many electrons must it hold? Well, we know the energy level holds 8. We know the s holds 2 of them. So it's going to hold 6. And you can see I've put the maths in red, but it is relatively straightforward. A p sublevel holds 6. We're also told that a p sublevel is made up of 3 orbitals. So based on that, how many electrons do we think an orbital can hold? I've actually already discussed this. We have got 3. In fact, hang on. So just amended that. I was answering a different question. There are 3 orbitals holding 6 electrons. Each orbital holds 2. That is always true for an orbital. And this will develop, your confidence, your understanding will develop when we start to put together some of the electron configurations. If we move on to principal energy level 3, we've got a 3s sublevel. Have a think about how many that contains, try the rest of the questions, pause and review when you're ready. So a 3s sublevel where we know that s sublevels contain 1 orbital and we know that 1 orbital can hold 2 electrons. We also know that it's going to have a p sublevel, and we have already established that that means it's got 3 orbitals. Each orbital can hold 2, so that's a total of 6. But we're now going to introduce the D sublevel. And within the third principal energy level, there is a D sublevel. It's made of 5 orbitals. So how many electrons do we think it can hold? Well, remember that an orbital always holds 2. That means 10 electrons. Okay, moving on to writing electron configurations. So have a read of this. I'm going to give you a diagram. I'm going to build up the diagram that it's discussing, and then we're going to look at how we can use that diagram. See, this is much more complicated than we have seen before. You need to remember that we fill the sublevels in a particular order, and it's not as straightforward as you might think. The diagram I am putting up here with my 1s, 2s, 3s, 4s, I put next to that 2p, 3p, 4p. I then do 3d and 4d, and I do 4F, will always be a go-to if you get stuck. If you sketch that, you can work out the order in which we fill. We're never going to go higher than 4p. That's krypton. That's 36 electrons. You put the arrows in backwards, diagonally down, and you can see we fill 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p. So it wouldn't necessarily work in your mind logically. You might think that you would do 3d before 4s, and it's absolutely vital that we get that the right way round. So now we have an opportunity to try to write out some electron configurations. There's a how-to guide here where one of them has been done, and I'm going to recommend you try them, and then we will review. So the first one has been done for you. Hydrogen has got 1 electron. We know that we fill 1s first. That means we put 1 in the 1s. We've got our 1s for the sublevel and 1 as a superscript for the 1 electron. If I move on to lithium, lithium has got 3 electrons. I know that 1s can hold 2. After 1s, I move to 2s. I've got 1 left, so it becomes 1s2, 2s1. Nitrogen has 7. So I put 2 in 1s, 2 in 2s, and that leaves 3 in 2p. I've gone 1s, 2s, 2p. For the next one, aluminium with 13 electrons, we're jumping up a little. We've got 1s2, 2s2, 2p6, 3s2, and then we're jumping into the 3p1. You can count up these numbers, 2, 4, 10, 12, 13, to know we're getting to the atomic number. Argon. We have got 1s2, 2s2, 2p6, 3s2, 3p6. Going to go through these a little quicker now, because hopefully you're getting to grips with them and you can see if you've made any errors. So vanadium, which has got 23, remember we fill 4s before we fill 3d, as this diagram shows. So we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Cobalt has got 4s2, 3d7 at the end, and you can count it up. It's 7 across in the transition metals. When we get to gallium, we're moving much, much further over, and we get to 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. You will be expected to do any or all of these in an exam. For selenium, slightly bigger again, that goes as far as 4p4, and krypton is the biggest one you are likely to have to write out, and that takes you all the way up to 4p6, 36 electrons. So the added complication that we have is that there are different ways of showing electron configurations. That's the longhand version, and we're now going to look at shorthand. Pause, have a read through the blue box, try these 3 examples, and then we'll see how you've done. Okay, so we're going to take a look at lithium first. We know that lithium has got 3 electrons, but in the shorthand, what we do is take away the beginning of the configuration and replace it with the noble gas that precedes the element we're looking at. So lithium with 1s2, 2s1. Helium has the electron configuration of 1s2. So instead of writing 1s2, we put the helium in square brackets, and then we add the 2s1 on the end. That doesn't seem like shorthand, I appreciate. But when you get to bigger atoms, bigger elements, it becomes more useful. So for argon, we've got 1s2, 2s2, 2p6, 3s2, 3p6. Actually, because it's a noble gas, its noble gas shorthand configuration is simply Ar in square brackets. But if we take a look at cobalt, and cobalt has got 1s2, 2s2, 2p6, 3s2, 3p6, we can substitute all of that with argon, because that's the electron configuration of argon. And then we add the 4s2, and we add the 3d7. So you can see the shorthand version right there. And then we have an additional consideration, because we can write them in longhand, we can write them in shorthand, or we can actually write them in a more complicated way. It's actually really important. There's a reason that we do this, and we're going to talk about Hund's rule. But I'm going to ask you to think about the general questions on here. This might not be you. Think about how people generally respond. They get on a bus, there are seats available, where do they sit? The reality is, you're going to take your own double seat rather than sit next to a stranger. And then what can often happen is you have to share your seat as the bus fills up, but you notice, and you can watch this if you see people on the bus, they tend to align themselves away from each other. One person might lean into the window, one person might put their feet out into the aisle, and they're almost minimising the opportunity for them to contact. They're repelling each other in the nicest way. So how does that fit with what we are going to look at? Well, we've spoken about principal energy levels, sublevels, and orbitals. We're now going to need to delve a little deeper into orbitals. Electrons will repel each other within an orbital. Those pairs of electrons, just like two people, will repel each other if they're strangers sat next to each other on a bus. So what they will also do is fill up the orbitals one by one. And we'll see what that means in some examples in a second, but they will only share when they absolutely have to. So I want you to take a look at each of these examples and try to write out the electron configuration, taking into consideration orbitals. And I'm going to put the first example up. So aluminium, I've got 2 electrons going into 1s, 2 electrons going into 2s. My next 3 electrons each take 1 orbital apiece, just like each person would take a double seat each on the bus. And it's only then the next 3 electrons would go in to complete the 2p. At that point, the 2 more electrons go into 3s, and then we have got aluminium going to 3p1. So 1 electron in 1 orbital. So have a go at the next 2 and we'll review the answers. Okay, a little bit simpler. Lithium has got 3 electrons, so I fill the 1s, I put 1 in the 2s, and we're done. Beryllium has got 4 electrons, so I put 2 in the 1s, 2 in the 2s, and we're done. Now let's look at some slightly more complicated ones. These are not completed. You'll need to go beyond 3D, certainly on the last one. But have a go at these 3 examples and let's see how you do. So nitrogen with its 7 electrons is going to go 1s2, 2s2. I have 3 more electrons. They are each going to take a p orbital each. So they're not going to double up, they're not going to share. For calcium, well, actually, the calcium, I am going to add in all of them and go right to the end because it goes to 4s2 and it fills every single sublevel. But if we delve a little deeper into germanium, I've got my 1s2, 2s2, I put 3 into my 2p sublevel, my 2p sublevel then gets the remaining 3, then the 3s fills up, I put 3 into my 3p, I then fill up my 3p, I fill up my 4s, and germanium has got 2 left, so it ends in 3d2. We also need to consider what happens with the electron configuration of ions. So I would like you to have a read through, try these, and then review your answers. In the first instance, I've not put the correct answer down yet. These are the atom electron configurations. But when we get to the ion, to get to, in each of these cases actually, a full outer shell, we know that O2 minus is gaining 2 electrons, fluoride is gaining 1 electron, sulfide is gaining 2 electrons, then actually what we end up with is this. And what you'll notice is they all look identical. They're all isoelectronic species, which is a term we're going to talk about in a moment. And then we take a look at further examples, slightly more complicated with positive ions. Have a read of this carefully, try it, and then we can review. So I've started by adding the actual electron configurations. There is a copper anomaly, which you may well have studied. It may be that you don't discuss it until year 13, but it's actually 4s1 3d10, not 4s2 3d9. Chromium has a similar thing where it goes to 4s1 3d5. But how do we amend them? Well, the big thing that I want you to remember is that you fill 4s before you fill 3d, but you empty 4s before you empty 3d as well. Now, what that means is for scandium, we're losing 2 electrons, we lose the 4s2, so it becomes 4s0. For the iron, we're going to lose the 4s2, and we lose one of the 3ds to go down to 3d5. In copper, we're going to lose the 4s1. For titanium plus 4, we lose 4s2 and we lose 3d2. It actually stops at 3p6. And for cobalt, losing 3 electrons, we lose the 4s2 and we lose one of the 3ds, taking me down to 3d6. You don't have to include the 4s0. You could simply get rid of it. But if you're working through this logically, you might find it helpful to do it. Final part of this section of the topic is isoelectronic species. Read through this carefully, have a go at answering the questions, and then we'll review. So identify a cation which is isoelectronic with neon with a charge of +2. So a cation is positive, and we are looking for something that would have the same electron configuration as neon after losing 2 electrons. That means the only answer we can give is Mg +2. O -2 is the anion that would give us the same electron configuration as neon. I've also put down here the 2 anions that are isoelectronic with krypton. So it could be Br- because the Br- has gained 1 electron to have 36 electrons, and Se2- has gained 2 electrons to have 36 electrons. And then you can go to your periodic table. It's not in the first 36, but going back to the 2 cations, for the same reason, Rb+ would have lost an electron to go down to 36. Sr2+ would have lost 2 electrons to go down to 36. Isoelectronic with krypton. There isn't one single answer for the next one, the common transition metal ions that are isoelectronic. I've picked manganese and iron. They're neighbours, they're right next to each other. If manganese loses 2 electrons and iron loses 3 electrons, they would both give the same electron configuration. So that takes us to the end of quite a weighty topic, quite an important topic. And hopefully, if you're happy with that, you're ready to move on to start using some of this information to look at ionisation energy. Thank you for listening.